Hey guys, thanks for tuning in. In this video, I'm going to talk about the chain rule. So what I'm going to start with is a surface that you saw in my previous video, and we're also going to compute the gradient vector. And this question asks us to show that if we're at the point 1, 1, f of 1, 1 on our surface, and we move in the direction of the gradient vector, we have to go up before we go down again. Well, part of that sounds like it might be kind of obvious because we know how the gradient vector is defined. The gradient vector tells us that if we're standing at a point on our surface, our first step is going to be in the direction of greatest initial increase. So we know that if we follow our gradient vector, that our first step is going to be uphill before we start to go downhill again. So let me come up with a parametric path, a two-dimensional parametric path that kind of captures the essence of what this question is asking. So it's saying, hey, suppose that we're starting at the point 1, 1, the x and y values x 1, 1 associated with our surface. So if our x value and our y value are both 1, then we can map that onto our surface eventually to the point 1, 1, f of 1, 1. And then we're going to walk in a line based on multiples of the gradient vector that we calculate at the point 1, 1. So we take our gradient compass out of our pocket and we see what direction it tells us to walk in, and we take a step in that direction. And as you guys might guess, if we plot our altitude versus time, so this function right here, or this graph right here, is a graph of f of x of t, y of t, versus t. So our altitude versus time. And you could see that our altitude is going to increase when we take our first step. Now, the thing that some students find surprising is that if we continue to walk along this line, eventually we start to go downhill again. And the question usually comes up as, well, wait a minute, the gradient points in the direction of greatest initial increase, so shouldn't I be walking uphill forever if I'm following the gradient? And the answer is not exactly, based on how this line was parameterized. We basically took our compass out of our pocket and we got a single compass reading. And then we just started blindly walking in that direction, and we never checked our compass again. We never readjusted. Well, if you take your gradient compass out once and get a gradient vector and walk in that direction and just never check and update the direction to walk in again, the most likely scenario is that your first step is guaranteed to go uphill, but eventually you're probably going to start to go downhill again because this local information doesn't tell you globally what's going to happen on the surface if you keep on walking and you don't think about what's supposed to happen. And I could actually illustrate that to you because I did go into your surface and I actually plotted this. So this is a plot of not x of t, y of t, but a plot of x of t, comma y of t, comma f of x of t, y of t. So I mapped this parametric path onto the surface, and we could see this first step is uphill, but then afterwards, eventually, we start to go downhill again. And that would be expected anytime we check our gradient vector once and then never again. So let me try to put all this together because there's a lot of stuff flying around right now. We have our equation for our surface. You want to imagine that that's like a mountain in a national park. And then we have our x of t, y of t, which is a two-dimensional curve. You want to imagine that you've gone to the national park office and you ask someone working at that welcome center, hey, can I have a map of the national park? And they might hand you a hiking trail map where they say, yeah, here's a really good trail map. This is a really good beginner's hike for you to take. You should try this one out or something. And so it comes on a flat sheet of paper. So it's a two-dimensional representation of something that exists in three-dimensional space. Well, actually, if you look at how this hiking trail maps onto the surface, it doesn't really look like a hike for beginners. That looks like it would be pretty darn tough. Well, how do we go from the map to the actual hiking trail? We would take our x of t, comma y of t, and then we'd add comma f of x of t, y of t. We map our path onto the mountain, onto our surface, and that gives us a parametric path on our surface. This is the difference between how the hiking trail looks on a sheet of paper versus how you'd actually experience it in the real world. So the red curve is the map, and the blue curve is what you'd actually experience. And if you live in a place like Illinois, the difference between the two, not so great. But if you live in Colorado or something, the difference between what you see on a sheet of paper and what you actually experience when you start walking on that mountain, you're like, oh, this thing that looked like a nice little simple loop actually has required me to climb up this entire peak and then back down again. This was a pretty tough hike because there's change in altitude, and change in altitude can keep you pretty busy. So to summarize here, we want to think of x comma y comma f of xy as our surface or a mountain. We want to think of x of t, y of t as a two-dimensional parametric path, which is our map of a hiking trail. And then we want our x of t, y of t, comma f of x of t, y of t to be a parametric path that's actually on our surface. That's the actual hiking trail that you really end up walking as opposed to what you see on that paper map. All right, well, now I could add some gradient vectors to my map. So I could add some compass readings to my map, and it would look like that. Now, these I just kind of threw in there. The gradient vector doesn't actually live in three-dimensional space, it lives in two-dimensional space. But if you imagine yourself as a little person walking on this surface and you're taking that gradient compass out of your pocket and checking it occasionally, those are, the compass readings that you would be getting. Those are where the needle would be pointing on your magical compass as you're hiking on that mountain. So again, you really want to think of your surface like a mountain. And you want to think of your parametric path as a hiking trail on that mountain. And then you want to think of your gradient vectors as basically readings from a magical compass that tell you where to go if you want to walk in the direction of greatest initial increase on your surface or on your mountain. And now that we have this picture, it's getting a little complicated, but now that we have this picture, we could try to figure out how steep the road ahead is based on our compass readings. So I'm going to try to simplify this picture. There's too much going on here. I've got like a surface, 3 dimensions, and then I've got a map in 2 dimensions right below it. There's too much going on here. So let me just take the 2-dimensional picture. So now you're looking at your 2-dimensional map that you picked up at the Welcome Center for the National Park. And what I've plotted is my parametric path x of t, y of t, and a couple compass readings at various points along our parametric path, and some orange tangent vectors. So the blue vectors are gradient compass readings, and the orange vectors are tangent vectors, basically pointing in the direction we're walking on our hike, like showing us what direction we're going to walk on this loop as we're going on our vacation or whatever. Okay, so let's go point by point and try to figure out what's happening on this hiking trail. And I think the easiest point to figure out what's going on is right here, because you'll notice that our tangent vector is pointing in the same direction as our gradient compass. And so what that tells us is that at this point on our surface, we're walking uphill as steeply as possible. When we're walking in the same direction as the gradient vector, that means that at this particular tiny little moment in time, we're walking uphill as steeply as possible. That's in contrast to this lower right-hand corner here, where we have the opposite of that happening. The direction we're walking in, the orange tangent vector, is pointing in the opposite direction as our compass reading. Well, if uphill is behind us and we're walking away from uphill, we're walking downhill. And not just downhill, we're walking downhill as steeply as possible. So here, we're walking downhill as steeply as possible at that particular point on our hiking trail. And then we have 2 other ones to figure out. This one's kind of interesting. Now, I didn't get it perfect when I was making this image, but this is supposed to look close to a 90-degree angle. I know it's not quite perfect, but it's about a 90-degree angle. Well, if uphill is to our left and we're walking kind of perpendicular to uphill, well, perpendicular to uphill is walking level. And you can kind of imagine how that would play out if you can, imagine a surface here. Let's say we've got our mountain here. And you're hiking on that mountain. and you check your magical compass, and it tells us that uphill is this way, but we're walking perpendicular to that. Oh, okay, so if we're not going uphill as steeply as possible, but perpendicular to that, we're walking level. So at this brief moment in time, we are walking level on our surface. And then finally, there's one more pair of vectors to compare here. It's just right here. And in this case, we have to be a little bit more careful because we don't have, just in the same exact direction or opposite directions or 90-degree angles. This angle right here, we'd have to categorize it as, is this an acute angle or an obtuse angle? And if you guys were in class with me, I would ask you, but instead I'm just going to tell you it's an obtuse angle there. And so what that tells us is that we are walking more against the gradient vector than with the gradient vector. And so if we're walking against the gradient vector, we're walking against uphill. And if we're walking against uphill, we are walking downhill. Or if you want to phrase this in terms of kind of a calculus idea, df dt is negative. We're walking downhill. Our change in height on our surface is negative. We're walking downhill. Now, are we walking downhill as steeply as possible here? No, because the gradient vector is not at our back, but we do have an obtuse angle here, so we're walking more against the gradient vector than we are walking with it, so we're walking downhill. Now, what's kind of cool is what we observe is that the angle between the gradient, df dx, df dy, and the tangent vector, x prime of t, y prime of t, is key to what's going on here. So, by the way, these orange tangent vectors, the equation for those is x prime of t, y prime of t, and the equation for these gradient vectors is df dx, df dy, or partial fx and partial fy. Anyway, so the angle was what mattered, right? Like we had this obtuse angle right here, and that's what we cared about, the obtuse angle between the gradient vector and the tangent vector. Well, we've just spent entire chapters of material learning about vectors and the relationships between vectors and how to categorize those relationships. We're going to use that information now, right? There was a reason we were learning that. Remember that we have this dot product formula that says that the dot product of two vectors is the magnitude of the first times the magnitude of the second times the cosine of the angle between those two vectors. The dot product gives us information about the angle between two vectors. When the dot product between two vectors is positive, the angle between those two vectors is acute. When the dot product between two vectors is negative, the angle between those two vectors is obtuse. And so if we're trying to classify obtuse and acute angles between vectors, the dot product is going to do that work for us. So what we can say is that if the angle between the gradient and the tangent vector is acute, that means the dot product between those two vectors is positive and we're walking uphill. Likewise, if the angle between the gradient and the tangent vector is obtuse, the dot product between those two vectors is negative and we're walking downhill. So there's those two correspondences again. Well, let's try to formalize what uphill and downhill means. I already kind of alluded to it earlier. But walking uphill is like saying that f of x of t, y of t is increasing at our particular moment in time. And walking downhill is like saying that our function, our altitude, is decreasing at that time. And let's put it all together. That means that df dt is equal to the dot product between the gradient vector and the tangent vector at that particular time. And this is called the two-dimensional chain rule. Pretty cool. df dt is equal to gradient dot tangent. We could lift this up to any number of dimensions. So this two-dimensional chain rule, it corresponds to the chain rule that you learned from your Calc BC teacher last year. But we could also lift it up to 3 dimensions, n dimensions. This is a chain rule that will work in any number of dimensions, which is kind of neat. Even the one-dimensional case, you guys could see right here, this is the same chain rule that I wrote above, just in one-dimensional space. And what is this? Well, look, it's derivative of the inside times derivative of the outside. Oh, that's just chain rule. So our one-dimensional chain rule does connect to the two-dimensional, three-dimensional, and n-dimensional chain rules. Now, when you guys were in your Calc BC class, your teacher probably said, oh, the chain rule is derivative of the outside times derivative of the inside. But now we're in a multivariable calculus class, and in the multivariable context, derivative of the outside is now the gradient, times is now the dot product, and the derivative of the inside is now the tangent vector. And you guys could see it happening up here, right? Look at this two-dimensional chain rule. So the derivative of the outside for f is going to be the gradient of f. The derivative of the inside, well, what's inside this function, x of t, y of t? Oh, the derivative of the inside is the tangent vector. And then we don't have multiplication, but we do have the dot product here. So last year's derivative of the outside times derivative of the inside still applies to this year's chain rule, but now it's gradient dot tangent. And now that we have this chain rule at our disposal, we could prove that the gradient vector is always perpendicular to the level curve passing through its tail. So I'm going to say that, suppose I have some surface, z equals f of xy, and we have some level curve. Well, what is a level curve? We take our surface and we set it equal to some horizontal tangent plane. Well, some horizontal tangent plane z equals a constant, O. So we set f of xy equal to a constant there. That's how we get a level curve. Anyway, let's suppose that we have some level curve that we can parameterize. Let me draw one for you. Let me trace one. Because the picture you have here is a contour plot with lots of level curves. We're going to prove this for a single level curve, but we're going to do it in general so that it applies to all level curves. So there we have a level curve. And what we're going to prove is that that level curve is perpendicular to any gradient vector whose tail is on that curve. Okay, well, let's suppose that I can parameterize this level curve as some x of t, y of t. Well, then a tangent vector on our level curve, if the level curve is parameterized as x of t, y of t, the tangent vector would be x prime of t, y prime of t, right here. And then our gradient vector is df dx, comma df dy, right here. And, well, we want them to be perpendicular. We want these two vectors to be perpendicular. You guys already know a condition for proving two vectors perpendicular, and that is if their dot product is 0, that means that they're perpendicular to each other. So we want df dx, comma df dy dotted with x prime of t, y prime of t to equal 0. We want gradient dot tangent to equal 0. But wait a minute, we just proved this, or we just came up with this chain rule on the previous slide. So by chain rule, I know that this dot product is df dt, the change in altitude on my surface for the path I'm walking, right? df dt, the change in altitude as I walk along the path x of t, y of t. But what path am I walking? It's this red thing on the screen right here. Well, this path is a level curve. The thing that's special about this parametric path is that as I walk this path on our surface, as I go on this hike around my mountain, my altitude is not changing because the curve was found from c equals f of xy. F of xy equals a constant. My altitude is equal to a constant. So because c equals f of xy, and we know that the derivative of a constant is 0, since the derivative of a constant c is equal to 0, I could put a 0 in there. And wait a minute, that's exactly what I wanted to prove. Now I know that gradient dot tangent is equal to 0. I just proved that the gradient is perpendicular to the level curve. The gradient vector is always perpendicular to the level curve passing through its tail. All right, so there it is. I can also show you guys how to use the chain rule to crunch some numbers, so you'll see these come up occasionally. So if I give you some surface, It's a new surface here. I made up a new equation. And I give you some parametric path. Just keep in mind that this surface is kind of like some mountain, some sort of geological formation, some sort of national park that you can go for a hike there. And then your x of t, y of t is some parametric path that you can map onto that surface. So it's a hiking map that you can pick up from that national park office. So when you're asked to compute df dt, what you're really being asked to compute is as you walk along this hiking trail, what is your change in altitude with respect to time as you're walking on that hiking trail? Now we can compute the gradient. So here's the gradient of f. So I just need df dx comma df dy. So I get some partial derivatives here. Now I'm not going to leave this in terms of x's and y's. I'm going to write this as 2x of t plus y of t, comma x of t. And when I plug in all of the appropriate values for x of t and y of t, I get this function in terms of t. Same idea here for x prime of t, y prime of t. I'm going to take my x of t, y of t that I have above. I'm going to take the derivative of each of those terms, and I'm going to get negative sine of t, comma cosine of t. Now, the chain rule tells me that the df dt that I'm looking for is going to equal gradient dot tangent. But I want to make sure that this is all in terms of t's. So this gradient vector here, I'm going to plug in the version that has t's in it. I'm not going to leave x's and y's in my final answer. So the dot product I'm going to take is this 2 cosine t plus sine t, comma cosine t, dotted with my tangent vector, negative sine of t, comma cosine of t. Take our dot product. And if you're a big fan of trig identities, as I am, you could write a really nice looking final answer, cosine of 2t minus sine of 2t. If you don't like trig identities, you could leave the answer as the previous step, and that would be perfectly good as well. And what does this represent? This df dt tells you your change in altitude on the curve at a particular t value. So you plug in a t value, and you get your df dt at that particular moment in time, at that particular location on your hiking trail. You get your df dt for that spot. Okay, another question that you could be asked, let's say here's another surface that I made up here, and let's suppose that you're standing on the surface at the point 2, 3, 20, right here. And you don't take out your gradient compass or anything. You just decide, I'm going to walk in the direction of the vector -7, 2. I'm not taking out my gradient compass. I'm not going to guarantee that I'm walking in the direction of greatest initial increase. I'm just going to pick a direction to walk in. And I want to know, am I going to walk uphill or downhill when I take my first step? Well, really the question boils down to, am I walking with or against the gradient vector when I walk in the direction of -7, 2? If I'm walking with my gradient vector, I'm going to go uphill. If I'm walking against my gradient vector, I'm going to walk downhill. So I should compute my gradient vector, and that should give me my answer. So here's my gradient vector. Now I'm standing at the point 2, 3, 20, so I'm going to replace the x's with 2's and the y's with 3's, and I get the gradient vector at this particular point is 9, 24. This is my compass reading that tells me the direction of greatest initial increase on my surface. So if I could figure out if -7, 2 is with or against that compass reading, I'll know if I'm walking uphill or downhill. And this is the same concept as the chain rule. We're going to use the dot product to do all of the heavy lifting here. If this dot product ends up as positive, I'm walking uphill. If this dot product ends up negative, which in this case it is, I'm walking downhill, because that negative reading tells us that I'm walking against the direction of the gradient vector, meaning that first step that I'm going to take is going to take me downhill. Now, this is for my first step. Who knows what's going to happen 10 steps from now? But that very first step, I know that I'm going to walk downhill for that first step in the direction of the vector -7, 2. This should be very similar to the intuition that you guys saw from the chain rule. By the way, if I try to capture this as a two-dimensional image, I have my contour plot right here. Here's where that little stick figure was standing. And what you can see is, here's the vector -7, 2. This is the direction I'm actually going to walk in. And then here's my gradient vector, and what you'll see is an obtuse angle between my gradient vector and my, I guess, tangent vector, but it's not exactly a tangent vector. It's just the vector that I'm going to walk in the direction of. So it's not a tangent vector to some curve, but still, there's an obtuse angle between the direction I'm going to walk in and the gradient vector, which means that I'm going downhill. And you can really see it in this contour plot, right? You can see that the gradient vector is pointing uphill here. You can see these levels as the colors are getting lighter. That's representing basically higher and higher altitudes. And then as the colors get darker, that's representing like deeper and deeper into the ocean. So the orange vector is walking downhill, deeper into that surface, and the gradient vector is pointing uphill. And since we have that obtuse angle between the two, we know that this orange vector is going downhill. It's going to take us downhill when we take our first step at least. Guys, I hope you enjoyed this video. Tune in for more videos about gradient vectors and contour plots. I have 2 more videos coming.